Like the first generation of onboard diagnostics, OBD II checks sensor and actuator circuits for opens, shorts, and out-of-range values. However, this is where the similarity in diagnostic capability ends. This is because OBD II is programmed to test components and subsystems for progressive deterioration as well as gross failures. The PCM contains a sophisticated software program which is responsible for conducting diagnostic tests on every component that affects emissions. These diagnostic tests are called monitors. Currently, there are 13 monitors. 8 of these are common to all OBD II vehicles produced since 1996, including comprehensive components, misfire detection, fuel control, exhaust gas recirculation or EGR, catalyst efficiency, oxygen sensor, O2 heater, evaporative emissions or EVAP. The following 5 monitors are used on specific applications: AC refrigerant, heated catalyst, positive crankcase ventilation, secondary air, thermostat. Monitors are classified as being continuous or non-continuous. As the name suggests, continuous monitors run all the time once a specific set of conditions have been met. There are 3 continuous monitors, including comprehensive components, misfire detection, and fuel control. The remaining monitors are non-continuous since they only run once per trip. This means that after the necessary conditions have been met and the PCM runs the test, the monitor will not run again until the appropriate conditions have been met on the next trip. As previously mentioned, a specific set of conditions must be satisfied before the PCM will execute a given monitor. For example, the vehicle may need to be operated at 55 miles an hour for 3 minutes in high gear. In addition, the engine may be required to be within a certain temperature, load, and speed range, and no related DTCs can be stored and no conflicts exist. These conditions are collectively known as enable criteria. Once all of the required conditions have been met, the PCM will run the monitor. The enable criteria for any given monitor can be quite extensive and will vary from one control unit to another. Here's an example of the enable criteria that may be required before the EGR monitor will run. VSS, 55 to 60 miles per hour for 10 minutes. TPS, 1.5 to 2.2 volts, steady throttle. Engine load, 2.0 to 3.3 ms. ECT, above 180 degrees Fahrenheit or 82 degrees Celsius. Gear position, high gear. RPM between 2,000 and 2,400. No pending conditions. No conflicts. Before the PCM runs a monitor, it must determine if any unresolved failures exist that would interfere with the proper execution of the test. These unresolved failures are known as pending conditions. For example, running the catalyst efficiency monitor when a code is stored for a defective post-catalyst O2 sensor would be counterproductive, since the PCM relies on the pre- and post-cat O2 sensors to evaluate converter performance. Consequently, the PCM will delay the execution of a given monitor anytime a failure has been detected in a related system. Here's an example of several pending conditions that would prevent the PCM from running the catalyst efficiency monitor. Misfire detected. O2 monitor failed. Fuel control monitor failed. Pre- and post-cat O2 electrical failures, or CCM. ECT failure, or TPS failure. A conflict exists anytime the PCM attempts to execute a given monitor while a related monitor is already in progress. A conflict also exists if separate controllers see different data concerning a shared sensor input. Checking for conflicts beforehand prevents the PCM from failing monitors incorrectly. The PCM executes the monitors according to specific strategies, including passive testing, active testing, and intrusive testing. Passive testing is a wait-and-see strategy used by the PCM to identify obvious systems failures, such as an open or shorted sensor circuit. With active testing, the PCM takes direct control of a device or devices in order to gauge the reaction of suspect components or subsystems. For example, The PCM may increase fuel delivery in order to evaluate the response time of the O2 sensor. Active tests go undetected by the driver and are often performed due to a failed passive test. An intrusive test is essentially an active test with one significant difference. Intrusive tests typically have an adverse effect on drivability and emissions. Consequently, it's possible for an intrusive test to be mistaken as an intermittent drivability problem. Keep that in mind when diagnosing an alleged intermittent. Readiness status is one of the required test functions for a scan tool. In this mode, all of the system monitors will be displayed along with corresponding messages indicating if the tests have been run. Keep in mind that readiness status does not indicate whether a given monitor has passed or failed, only if the PCM has executed the test. The messages used to indicate readiness status vary among scan tools. For monitors that have run, the scan tool should display COMPLE or complete. The following scan tool messages are typical for monitors that have not yet run: penned or pending, or incomplete. If a particular monitor is not used on a vehicle, the scan tool may display not supported. Because the continuous monitors are run repeatedly throughout the trip, the scan tool will always display them as being ready. However, non-continuous monitors may not be set to ready if the driver doesn't operate the vehicle in a way that satisfies all of the necessary enable criteria. Additionally, the scan tool will display the non-continuous monitors as not having run if the battery or PCM is disconnected, or if the DTCs have been cleared using the scan tool. Monitor readiness status is an indication of whether the PCM has tested all of the vehicle's emission controls. In states using OBD II IM, that's inspection maintenance test programs, one or more monitors displayed as not ready may cause the vehicle to be rejected for the test. Readiness status is one of the required test functions for a scan tool. In this mode, all of the system monitors will be displayed along with corresponding messages indicating if the tests have been run. Keep in mind that readiness status does not indicate whether a given monitor has passed or failed, only if the PCM has executed the test. The messages used to indicate readiness status vary among scan tools. For monitors that have run, the scan tool should display COMPLE or complete. The following scan tool messages are typical for monitors that have not yet run: penned or pending, or incomplete. If a particular monitor is not used on a vehicle, the scan tool may display not supported. Because the continuous monitors are run repeatedly throughout the trip, the scan tool will always display them as being ready. However, non-continuous monitors may not be set to ready if the driver doesn't operate the vehicle in a way that satisfies all of the necessary enable criteria. Additionally, the scan tool will display the non-continuous monitors as not having run if the battery or PCM is disconnected, or if the DTCs have been cleared using the scan tool. Monitor readiness status is an indication of whether the PCM has tested all of the vehicle's emission controls. In states using OBD II IM, that's inspection maintenance test programs, one or more monitors displayed as not ready may cause the vehicle to be rejected for the test. A misfire can be broadly defined as being either a partial misfire or a total misfire. A total misfire is a complete lack of combustion. Under this condition, the air-fuel mixture leaves the cylinder unchanged. Consequently, the cylinder makes no contribution to engine power. In the case of a partial misfire, combustion is incomplete. This causes the cylinder to generate only a portion of its potential energy. Whether partial or total, misfires not only result in reduced performance and increased emissions, but pose a serious threat to the catalytic converter as well. This is due to the excessive heat produced when the unburned mixture from a misfiring cylinder ignites inside the converter. Converter temperature is further amplified due to the response of the closed-loop system. During a misfire, unused oxygen is released into the exhaust. This causes a reduction in O2 sensor voltage, which the PCM interprets as a lean condition. As a result, the PCM increases injector pulse width, causing additional fuel to enter the converter. Misfires fall into one of 5 categories, including mechanical, electrical, lean, rich, and density. Mechanical misfire. Efficient combustion requires cylinders to be properly filled, sealed, and scavenged. Any breakdown in this series of events will cause the affected cylinder to misfire. For example, if the intake valve fails to open due to a worn cam lobe, the cylinder will not receive the volume of mixture required for proper combustion. If the cylinder is leaking because of a blown head gasket, for instance, the mixture will not be adequately squeezed during the compression stroke. Under this condition, the piston will be unable to compress the mixture sufficiently to produce the required increase in cylinder pressure prior to ignition. Finally, unless combustion byproducts are quickly discharged from the cylinder during the exhaust stroke, the incoming air-fuel mixture will become displaced by lingering gases incapable of supporting normal combustion. Consequently, an inactive exhaust valve is another potential cause of a mechanical misfire. Electrical misfire. Unlike a diesel engine, cylinder compression in a fuel-injected engine is not sufficient to ignite the mixture under normal conditions. Consequently, gas engines rely on a high-voltage spark to initiate the combustion process. An electrical misfire occurs when one or more spark plugs fail to fire. Electrical misfires are most common on engines that use spark plug wires, since the secondary cables are typically the weak link in the ignition system. Lean, a condition caused by unmetered air entering the combustion chamber, causing the air-fuel mixture to have significantly more air than desired when spark is initiated. The mixture has no conductivity, thus causing a lean misfire. Unmetered air is air that is not accounted or measured for by the MAF sensor. Typical areas for unmetered air to enter are leaking intake manifold gaskets, leaking injector O-rings, cracked or loose vacuum lines, and cracked or leaking exhaust manifolds or system pipes in front of the pre-catalyst heated oxygen sensor. Rich, a condition caused by too much fuel entering the combustion chamber, causing the air-fuel mixture to have significantly more fuel than desired. When spark is initiated, the mixture is too dense and the spark cannot promote a flame, thus causing a rich misfire. Some examples of typical causes for rich fuel conditions are leaking injectors, stuck closed fuel regulator, engine oil for a leaking head gasket or intake gasket, ECT circuit or sensor failure. Density, a condition caused by too much recirculation of exhaust gases, not the intake airstream. This condition is typical on vehicles with EGR valves. Hyundai uses CVVT to fulfill OBD EGR requirements. Flooding the intake airstream with recirculated exhaust gases cause the combustion chamber temperature to lose combustion heat, which renders the AF mixture inactive because the density of the chamber has been lowered to a point where the flash or ignition for motion is not possible. Examples of typical density conditions are stuck-open EGR valve in Melco systems. As for CVVT systems, monitoring the EGR flow on the GDS should provide data to diagnose potential CVVT processing concerns. There are 3 types of misfires. Type A is the most serious condition, since it's based on a misfire that can raise converter temperature beyond 1800 degrees Fahrenheit. With the Type A misfire, the PCM will flash the MIL once per second and store a hard DTC and freeze-frame data on the first trip. Once the vehicle begins operating in a range where the misfire no longer puts the converter at risk, the MIL will stop flashing and remain on steady. Be aware that the EPA does not require the MIL to flash if the system has an alternate catalyst protection method. For example, on some vehicles, the PCM will disable the injector of the misfiring cylinder to reduce the risk of converter damage. That's why in some cases the MIL may not flash when a Type A misfire occurs, but rather remain unsteady. Type A misfires are typically caused by problems in the ignition system, such as an open or shorted plug wire or a defective coil. Type B misfire is a condition that can cause emissions to exceed 1.5 times the FTP, or Federal Test Procedure, standard, while the severity of a Type C misfire is based on emissions levels exceeding California IM standards. The first occurrence of either a B or C type misfire will result in a pending DTC with accompanying freeze frame data. If the misfire occurs on the next consecutive trip, the PCM will illuminate the MIL and store a hard DTC. Type B and C misfires will also result in an illuminated MIL and hard DTC if they occur on 2 non-consecutive trips within an 80-day trip window under similar operating conditions. Type B and C misfires are generally the result of a fuel control or EGR problem. There are 13 generic DTCs assigned to misfire detection. Depending on the application, the PCM will either store a DTC for each misfiring cylinder, up to 12 cylinders, P0301 through P0312, or simply store a P0300. This code indicates that a random or multiple cylinder misfire has been detected, which typically indicates that the misfire is not specific to a cylinder, but shared or common ignition components to cylinders. Diagnosing a problem with closed-loop fuel control requires a technician to determine if the source of the trouble is electronic or mechanical. This is typically accomplished using artificial enrichment or propane and enleanment vacuum leak. However, with OBD II, the fuel control and O2 monitors can isolate the problem automatically. In this section, we'll focus on the operation of the fuel control monitor. This is where the fuel trim comes into the picture. Fuel trim is an adaptive control strategy used by the PCM for adjusting pre-programmed injector pulse width. Short-term fuel trim, or STFT, allows for temporary mixture adjustments in closed loop and serves as the basis for long-term fuel trim, or LTFT, corrections. For example, if the mixture is biased lean due to an air leak, STFT will compensate for the imbalance by adding fuel or increasing injector pulse width. Fuel will continue to be added until the proper air-fuel ratio is restored or STFT reaches the limit of its control. LTFT values are stored in cells, each of which represents a particular combination of engine speed and load. As the engine operates within the parameters of a given cell, fuel delivery, or injector pulse width, will be based on that particular LTFT value. Fuel trim is displayed on the scan tool as a percentage. These valves are based on the input signals from the upstream oxygen sensor or sensors in closed loop. 0% indicates that the mixture is balanced and no adjustment is required to the pre-programmed injector pulse width. A negative percentage is an indication that the PCM is reducing injector pulse width to compensate for a rich exhaust, while a positive percentage means that fuel is being added to compensate for a lean exhaust. The adaptive values for STFT are erased when the ignition is turned off. In contrast, LTFT values are stored in the computer's memory and remain there until the PCM's memory is reset with a scan tool or continuous battery power is removed from the PCM. With a properly functioning engine in closed loop, STFT will typically fluctuate within a narrow range of plus or minus 3%. On V-type engines, the scan tool will display fuel trim according to cylinder bank, i.e. STFT1, STFT2, LTFT1, and LTFT2. Keep in mind that the adaptive control limits for fuel trim vary among PCM manufacturers. For example, on some PCM controllers, the LTFT may have control within a range of minus 35% to plus 35%.
while on another PCM controller, the LTFT will operate within a range of only minus 23% to plus 16%. These inconsistencies between PCM controller manufacturers also apply to STFT control. As the engine operates within the parameters of a given cell, fuel delivery will be based on that particular LTFT value. When STFT attempts to correct a mixture imbalance, LTFT will observe the short-term adjustment and gradually move in the same direction. If STFT is able to restore the mixture to the stoichiometric level, then LTFT will update the fuel delivery value for the appropriate cell or cells, and STFT will be reset.
The fuel control monitor analyzes the activity of short-term and long-term fuel trim on a continuous basis, making it a continuous monitor. If STFT and LTFT remain at their limits too long, as would be the case with a severe air leak, for example, the fuel control monitor will fail. If the monitor fails on 2 consecutive trips, the PCM will illuminate the MIL and store a hard DTC. Comprehensive Components Monitor, or CCM, is an OBD II diagnostic test designed to check the integrity of all input and output circuits, including sensors, switches, and actuators. The majority of these devices are not tested by other monitors. CCM input tests may use 1-trip or 2-trip detection logic. Generally speaking, opens, shorts, and functionality failures will result in a stored code and illuminated MIL after only 1-trip logic. However, rationality failures typically must be detected on 2 consecutive trips, or 2-trip logic, before a hard code is stored and the MIL is turned on. The catalytic converter contains small amounts of delicate metals that initiate chemical reactions. These metals include platinum and palladium for the oxidation of HC and CO, and rhodium for the reduction of NOx. 3-way converters contain another element called cerium. Cerium has the ability to store and release oxygen, which helps stabilize catalyst operation and enhance the effectiveness of the noble metals. The performance of a catalytic converter is dependent upon the air-fuel mixture. When the mixture is on the lean side at 14.7 to 1, the converter is more efficient at reducing HC and CO. However, lean mixtures cause an increase in combustion chamber temperature, resulting in higher NOx emissions. When the mixture is on the rich side of 14.7 to 1, combustion temperatures are much lower. This reduces NOx formation, but it makes it more difficult for the converter to oxidize HC and CO due to the lack of available oxygen. That's why a stoichiometric mixture is essential for the converter to operate at peak efficiency. The Catalyst Efficiency Monitor is a non-continuous test performed once per trip. Since there is a direct relationship between a converter's ability to promote chemical reactions and its ability to store and release oxygen, the monitor compares the signals from an upstream and downstream O2 sensor to evaluate converter performance. On a properly functioning system in closed loop, the upstream O2 sensor will switch rapidly above and below 0.450 volts. If the catalyst is at least 95% efficient at converting the exhaust gases, the voltage from the downstream O2 sensor will remain effectively flat by comparison. This is due to the stability of the oxygen levels in the post-converter exhaust gases. On a vehicle with a degraded catalyst, the post-converter gases will contain varying amounts of oxygen. This will be indicated by a significant variation in the frequency and amplitude of the downstream HO2S signal in the closed loop. Once the number of downstream cross-counts exceeds a predetermined level, the monitor will fail. For Hyundai vehicles, a failure of the catalyst efficiency monitor will occur on 2 consecutive trips, will result in a hard DTC and illuminated MIL. Important: be aware that a leaking exhaust system can affect the stability of the oxygen sensor signals and ultimately lead to a false monitor failure. In addition, the use of aftermarket components, such as a replacement converter or O2 sensor, may lead to a false DTC. The atmosphere is composed of 21% oxygen, 78% nitrogen, and 1% of other gases. Nitrogen is a colorless and odorless gas that is also non-reactive. However, This characteristic changes when combustion chamber temperatures exceed 2500 degrees Fahrenheit or 1371 degrees Celsius. Under this condition, the normally inert nitrogen becomes a reactive gas where it combines with oxygen to form a variety of pollutants, namely nitric oxide, or NO, and nitrogen dioxide, NO2. These compounds are collectively known as oxides of nitrogen, or NOx. When NOx and hydrocarbons merge in the presence of sunlight and still air, the result is photochemical smog. In addition to stimulating NOx production, excessive combustion temperatures also allow the mixture to ignite prematurely, resulting in engine detonation or spark knock.
Exhaust gas recirculation systems are designed to reduce NOx emissions by recirculating a small amount of exhaust gas into the intake. The variable valve timing system regulates the flow of exhaust gas to the intake manifold by changing the overlap time of the camshafts. Exhaust gas recirculation is effective at controlling NOx for two reasons. First, exhaust gas does not contain the oxygen necessary to support combustion. Second, diluting the incoming charge reduces mixture density, which allows the air and fuel to burn more slowly. This causes a reduction in cylinder pressure and helps lower combustion temperatures by as much as 300 degrees Fahrenheit or 149 degrees Celsius. Because NOx output is relatively small at idle or when the engine is cold, no exhaust gas is recirculated under these conditions. Rather, EGR is used under acceleration, except WOT, and part throttle conditions.
The orange box outlines the EGR operational programming of the PCM and for the EGR monitor. EGR is not always needed, but in this highlighted area, CVVT via communication from the PCM does perform actions to affect an EGR effect, which in turn reduces NOx emissions to levels of control by the catalyst. WOT is not a consideration for EGR because at this demand the driver is needing full power even though combustion chamber temperatures are at their highest. Although control strategies vary among vehicle PCM controller manufacturers, the purpose of the EGR monitor is to determine if gas flow is sufficient when the PCM commands CVVT to flow EGR. A failure of the EGR monitor on 2 consecutive trips will result in an illuminated MIL and a hard DTC. One monitor control strategy relies on the response from the fuel control system when the EGR monitor is executed. Once the enable criteria have been met, the PCM will disable the EGR valve. If gas flow was sufficient while EGR occurs, there should be a significant reduction in O2 voltage and an increase in STFT once the valve is closed. That's motor running active test. This is because there is more oxygen present in an undiluted air-fuel charge, or no EGR. For example, if the EGR passages were to be partially restricted, the mixture will only gain a slight amount of oxygen when the EGR is stopped. This will be reflected in only minor changes in O2 voltage and a slight increase in STFT. The EGR monitor looks for changes in manifold pressure to determine EGR flow rate. Under normal conditions, manifold pressure should increase significantly when the monitor is executed or EGR commanded. This is due to the high-pressure exhaust gas flowing into the manifold. The MAP sensor provides the rational testing information to the PCM as validation of EGR occurring and that a change in intake pressure reflected EGR flow. The evaporative emissions system, or EVAP, reduces a vehicle's overall hydrocarbon output by storing and purging fuel vapors. The centerpiece of the EVAP system is the charcoal canister, which stores fuel vapors when the engine is off. When the engine is running, the vapors are purged from the canister and burned in the normal combustion process. To ensure the system is operating properly, OBD II vehicles are equipped with an EVAP monitor. OBD II vehicles are equipped with enhanced and non-enhanced EVAP systems. An enhanced system includes the hardware and software for leak detection, while non-enhanced systems do not. Because enhanced EVAP was not a federal requirement until 1998, many earlier model vehicles used non-enhanced systems. The EVAP monitor on vehicles with an enhanced system performs purge flow checks as well as leak detection. On non-enhanced systems, the EVAP monitor simply checks for correct purge flow. On some vehicles with enhanced EVAP, leak detection is accomplished using a pump to pressurize the tank, lines, and canister under certain conditions. Like leak detection, there are several methods used for checking purge flow. On some systems, the EVAP monitor looks for a drop in short-term fuel trim, plus or minus, as the canister is purged. If there is no change or the reduction in fuel trim is not within a programmed tolerance, the monitor will fail. Other systems use a diagnostic switch to sense the presence of vacuum. The switch is located between the purge valve and the canister. When the PCM commands purge, vacuum is applied to the switch, causing it to open. This results in a 0-volt signal at the PCM, which it interprets as purge flow. Important. On vehicles with enhanced EVAP systems, the MIL may come on, EVAP monitor failure, if the vehicle is refueled with the engine running or the gas cap is not fully tightened. This is the most common cause of EVAP DTCs.
Diagnosing a problem with closed-loop fuel control requires a technician to determine if the source of the trouble is electronic or mechanical. This typically is accomplished using artificial enrichment, propane, and enleanment, vacuum leak. However, with OBD II, the fuel control and O2 monitors can isolate the problem automatically. In this section, we'll focus on the operation of the O2 monitor and the O2 heater monitor. Vehicles equipped with zirconia oxygen sensors generate a voltage by distributing oxygen ions, that is, electrically charged atoms, across a pair of platinum electrodes. One electrode is exposed to the atmosphere of 21% oxygen, while the other electrode is exposed to the exhaust gas. The electrodes are separated by zirconia oxide, which is an electrolyte that attracts oxygen ions. Since the atmospheric electrode is grounded by an abundance of oxygen, it becomes negatively charged with respect to the electrode in the exhaust system. This allows the sensor to produce up to 1 volt of electricity once it reaches a temperature of approximately 572 degrees Fahrenheit or 300 degrees Celsius.
The O2 monitor analyzes 3 areas of sensor performance, including response time, voltage range, and switching frequency, or crosscounts. Response rate represents the amount of time required for the oxygen sensor to recognize a rich or lean condition. To determine the response rate, the PCM commands an abnormal air-fuel ratio and then calculates the time it takes the O2 signal to move from 300 millivolts to 600 millivolts, or vice versa. A good sensor will typically switch from lean to rich or rich to lean in less than 100 milliseconds. The O2 monitor also keeps track of sensor voltages and switching frequency, or crosscounts. During the normal closed-loop operation, a good upstream sensor will produce a voltage that rises above 600 millivolts when the mixture is rich and drops below 300 millivolts when the mixture is lean. The voltage will also switch between these extremes 5 times per second or more. If response time, voltage range, and/or switching frequency are not within monitor fail thresholds on 2 consecutive trips, the PCM determines sensor performance has fallen off and will turn on the MIL and store a hard DTC.
In order to minimize hydrocarbon and carbon monoxide emissions during engine warm-up, it's important to get the engine into closed loop in the shortest time possible. This is accomplished using heated oxygen sensors. Heated sensors can be recognized by having 4 wires. 2 of these are for the sensor's signal and signal return circuits. The other 2 wires serve as the power and ground circuits for the sensor's heating element.
Depending on the PCM controller manufacturer, the heat monitor verifies the integrity of the element using several different methods. One of the most common is the time to activity test. This test determines the amount of time required for the oxygen sensor to produce a working signal to the PCM following a cold start. If the time exceeds programmed values after 2 consecutive trips, the monitor will fail, resulting in a hard DTC and an illuminated MIL. The oxygen sensors used in an OBD II system are identified according to their position in the exhaust and on V-type engines, their location relative to the number 1 cylinder, or bank 1. Oxygen sensors mounted ahead of the converters are known as upstream or pre-cat sensors, while downstream or post-cat oxygen sensors are installed behind the converters. Because many vehicles use more than 2 oxygen sensors, it's important to become familiar with O2 sensor identification. This will allow you to recognize the appropriate sensor when analyzing scan data. Be aware that the oxygen sensors are used as diagnostic inputs for other monitors, such as catalyst efficiency and EGR. Consequently, a stored DTC for a faulty O2 sensor or heating element may prevent the other monitors from running. This is why it's important to always correct component DTCs first whenever multiple codes are stored.